Hey everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. As always, we have our co-host calling in from Sendai, Japan. How are you doing today, Simon?
Doing very well, thanks, Dave.
All right, and everybody, our guest today is Mr. Jorge Serrano. He is the Director of R&D from Acustica Beyma, which is a company based in Valencia, Spain. That's pretty famous for anybody in pro audio, building drivers, compression drivers, a lot of transducers coming out of Spain. So Jorge, how are you doing today?
Good, Dave. Thank you very much, Simon. Pleasure to be here with you guys.
Okay, great. Yeah. So, anybody who's worked in pro audio and especially European market, they know Beyma very well. Pretty famous for your drivers. Maybe you could start with a bit of a history of Beyma. Tell us a bit about where the company came from and a bit about, the different technologies you guys are famous for.
Sure. Yeah, well, Acustica Beyma was born more than 50 years ago. It was back in 1969 when the founders decided to start the company focused on professional audio applications. The beginning of the company, since the beginning, the purpose is to manufacture, design also, and manufacture components, transducers for audio systems dedicated for professional applications. So it's real deep in our nature as a manufacturer, the professional field, to understand what are the needs, what are the standards, what are the requirements from a real professional audio system. And since that moment, we've been, improving a lot of things from the design perspective, from the manufacturing perspective. Of course, 50 years is a long time, but it is true that we have never stopped looking for improvements, better ways to design the transducers, looking for better ways to manufacture in a consistent and with a repeatability, which is our key factor in our industry. It's important to have very good performance, very good features, but it is also very important to understand that the professional requirements is to have a very consistent response along the production batches and with the time, the duration and reliability of the products.
Just out of curiosity, so Valencia has not just one famous speaker company, but is there a university or is there some kind of talent resource to get the people that can do production engineering and design engineering for speakers? Is there some special school there?
Well, there is actually a very good public university, is Universidad Politécnica de Valencia, and where including me, myself, and most of my colleagues at Beyma and also other companies in Spain and also outside of Spain, we have studied there in Universidad Politécnica. It's a very good university. The former program was telecommunications engineering, and they made a focus, a specialty on acoustics, and so they have been, let's say, giving a very good curriculum to the students, very good fundamentals of all the back, all the foundations on the really physics and mathematics behind all the acoustics. And it is true that the Valencia area is curious because there are several pro audio companies there. We have system manufacturers there. We have also some very good installers, very good contractors. So it is true that this inside Spain is a region with a lot of history in the audio segment compared to other parts which normally could be considered as Madrid or Barcelona, could be considered like, more important. But Valencia has been always the most important, I would say, ground for the audio industry in Spain. It's curious, but it is like that. I'm not really sure it is related to the university or these studies that maybe we have here, because this really comes from back old days. It's like I said, Beyma was starting end of the 60s, beginning of the 70s, the activities in export. But we have also DAS Audio, which is another very good, well-known brand in our field. We have Music Zone, we have BMV, which now is Links Pro Audio. We have several, and all of those companies, they started actually around the 70s. So it is not properly related to the university and the having or helping the people to study this, because these studies, I think, if I'm not wrong, they started around mid-90s, something like that, focused on the which it was when I started to study about this. Okay.
Yeah, it could be possible that the university saw that there was a need to develop talent in acoustics after there was some early innovators in the 70s developing industry, and then, hey, there's jobs in audio in Valencia. Let's give them some talent. So that's great. Okay, yes. So keep going with the history, or would you like to transition to some slides?
Yeah, no, exactly. The point about Beyma is that we are mainly manufacturing cone drivers and also compression drivers for high frequency units, also some direct radiation like tweeters. But yeah, our main specialty, our main strength is in the big format, low frequency and high frequency drivers. Okay. And yeah, in this sense, I prepared some slides about some own technology we have, some proprietary technology we have. We call it Maltcross. Okay. And yeah, if I can start sharing here, if it works properly, let's go. Okay.
Okay. Yeah, I can see it fine.
Okay. So Maltcross technology, it's a way to more efficiently transfer the heat from the coil. Okay. In general terms, it's a forced air convection circuit in order to help with the movement of the cone, of the moving parts, moving assembly, to help heat dissipation in the coil. Okay. And just to go a little bit from the fundamentals, we've been experiencing, we've been doing a lot of research during years in Beyma, and one important conclusion is that the main heat focus in the low or in a transducer is in the moving coil. Okay, you can put to the speakers, which is helping additional material like heat sinks or radiators to help heat transfer as well. But the focus, the generator of the heat is the coil itself. As soon as the electrical current is moving, it starts to increase the temperature, dramatically and very, very fast, in a very fast way. And this increase of temperature increases the resistance, the electrical resistance of the coil. And this is causing, of course, that the power is less, because it's inversely proportional to the resistance. And with the power, which is dissipated less, the SPL, the final dBs, which is what acoustic system is looking for. The final goal of our system is not power. The final goal is air pressure, is SPL. Okay, so this is the point. This is very basic, but this is like this. You can add with heat sinks, as I tell you, but what we've found very interesting was to focus on ways to extract the heat from the coil, which is the main point. Okay, so there are three basic ways to transfer heat. You have conduction, which is you help the body to get colder, to put in contact, you can put in contact with another one, which is colder, and then there is a conduction transfer. You have radiation, which is the energy emitted by the body, okay? And you have convection, which is the way where a fluid is helping to cool that body, okay? So conduction, unfortunately, is not possible because the coil is transporting the audio signal, and you cannot interfere.
You can't
So
interfere with the motor, yeah. Okay.
Exactly, because it will be, in fact, the most efficient way to get out the heat. Okay, if we could put some part, in order to transfer the heat, it would be fantastic. But then this is not so feasible. So radiation, there are some radiation transfer, of course, through the metal parts. The coil, is facing, in the high SPL drivers, the air gap is very, very narrow, very small, in order to achieve very high sensitivity in the drivers. You have a very, very little space between the winding of the coil and the metal parts. So there are some emission from the coil that goes through the iron, and there are some radiation in this sense. And then what we have more field to play is with the convection. Okay, the convection is helping us through the airflow, which is inside the speaker. As I told, when the moving part is moving, there is an airflow below the dust cap. All the air below the dust cap of the cone driver and within the air gap. In fact, you have an airflow. Okay. So you can play with that. There are some parts you can work about. This is nothing new because for decades, subwoofers have been using some kind of forced convection. Okay, opening, as you may see from 70s, drivers with opening in the pole piece, openings in the frame, in the basket of the driver. So this is something that is being used for decades. But then in 2008, we started with something more, let's say, innovative. Okay, we decided to create a way to move the flow in a certain manner, which is helping a lot. You can have the airflow in a way which is called laminar, where all the particles of the air are moving in a parallel path, like, all the particles go like in the same direction, okay? And then you can have another way of movement, which is called turbulent. Turbulent flow means that the particles are moving, not in a similar way. They are moving chaotically, each particle in one direction. And this is much more efficient for the transfer because you have more particles constantly helping to reduce the temperature.
There's
the body.
There's more bombardment and more surface area reacting with the heated surface and pulling away as it
exactly
turbulent air. Okay.
Mm-hmm, exactly. So here, I don't know if you can see, but what we made here back in 2008, it was to create some slots in the pole piece, in the top plate of the pole piece. This is an inner neodymium magnet circuit, so that the airflow was forced to move through those slots. Okay, and the air was affecting all the surface. But if we go back here, in the equation, you have A, which is surface. So the higher the surface you have in contact with the fluid, the better for reducing the temperature. So we changed the convection factor to a turbulent flow affecting 100% of the surface of the coil with this design. Okay, this was patented, and then we came in 2012. We made a certain evolution, improving this concept, and we call this Maltcross technology, and this is also patented by us. And this is the main concept, okay, behind the thing. The thing is to, let's say, make the airflow go in a certain direction that we want to, in order to cool the coil. If you can see here, the blue lines It's like how the air is moving inwards, okay, of the you can see the backplate motor, the air gap, and then you have these curved parts are like a diffuser. It's like a diffuser, so that the airflow is forced to move through this diffuser and goes directly towards the coil. Okay, this is helping also because this piece is made with a certain shape so that we create the turbulent flow, as mentioned, and this is affecting also 100% of the surface. Okay, so you can see a cut here of a driver with this technology inside. Okay, so this is basically how it works. The Maltcross technology, it's a forced air convection circuit which creates a turbulent flow, which is much more efficient. In fact, just to show some results, okay, here you can see a 12-inch woofer. Okay, this is a 12-inch mid-bass, very regular driver, with 2.5-inch coil, okay, 64 millimeters coil. So you can see with and without the blue curve is the Maltcross driver, and the green curve is without Maltcross. It's a similar driver, but without this technology. And this is the temperature. So you can see as soon as we increase the power in the driver, the temperature obviously is increasing, okay? So you can see you can get more than 30% of reduction in the temperature, which is a lot, okay? So you can work with a much lower temperature in the coil. This is, let's say, one of the effects. And the result, which is what, as I previously said, what we are looking for is that the system is having, let's say, more constant SPL. You can work two ways with this technology. I mean, in the final application, you can try to reach maximum power, dissipated power, in order to reach maximum SPL, or you can just keep a little bit more conservative with the power, because you know that you will get more SPL finally more constant. So here you can see, if you go with this configuration to the maximum power, 600 watts, and you can see that after 30 minutes, which the temperature is, normally it increases really fast, the temperature in the driver, in terms of seconds. The coil is really, really hot. I will show you some slides later, but it is true that it's like a asymptote curve, it's constantly growing the temperature, and it can until you get the thermal equilibrium of the whole assembly, because you have a lot of iron, you have a lot of aluminum in a driver. Until you get this equilibrium, it can last hours. Okay, it can increase, but very, very, very few. So we say in 30 minutes you can have more or less an approximate idea. And here you can see that we are talking about 2 dB less about power compression. Power compression, I don't know if you are familiar with this term, but the effect I mentioned before, when the temperature in the coil increases, the resistance increases, so you have less SPL. This is what we call power compression losses, because you have, theoretically, you can have a driver with, I don't know, 98 dB, sensitivity 1 watt, 1 meter, and then you apply the power you want to apply, and theoretically you have certain amount of dBs, I don't know, 130 dB, okay, in a real application. But because of the power compression, which is a real effect that is happening to every transducer, you get a loss, you get less dBs finally, okay? So you can
see the power compression is actually a drop in SPL.
Exactly, Simon. It is a real drop. In fact, this is very common for the guys that are working in audio gigs. You put on the system, and then some minutes later, the SPL has gone, has dropped, and then there is a need to increase again the fader. And this effect is real, and it's happening in every transducer, because this increase of resistance, in the coil, and you can see it's not insignificant. For this driver, imagine we are in the 500 watts. We are talking about a regular driver is between 5 and 6 dB drop of SPL. And with this technology we are talking about, we lose 2 dBs less. But this makes a difference. 3 dB is like doubling the power, 3 dB in acoustics is like you have twice the power. So 2 dB is not insignificant amount.
So if I read that right, at 200 watts, you reach steady state. You got 3 dB of power compression. You double that power to 400 watts, and you have 5 dB power compression. So you've lost 2 dB, but you only were going to gain 3 dB by doubling the power. So you've ended up pretty much where you started, even although you doubled the power. Is it read like that?
Yeah, exactly. Yeah. Okay. So, and here is an example. This is a real fatigue test, power test we made. Okay. This is the increase of temperature in the coil. This is a relative way to measure the increase of temperature. And as I told you, you can see in the time axis, you have 7,200, which is 2 hours. AES standard, we are in the professional field for transducers. The majority of the manufacturers we are based on the AES standard to let's say to give information in the datasheet. And this AES standard is like a accelerated power test. So this is a test where we apply ping noise, which is filtered between range. There is a bandwidth, frequency, which depends on the application, obviously. Okay, and then we apply some dynamics. There are 2 ways. Basically, there are the 2003 standard where we use a 6 dB crest factor, which is the dynamics of the signal. And the last revision of the standard is the dynamic is 12 dB crest factor, is higher dynamics. And now currently there are some interesting conversations in the AES committee about I don't know if you have heard about the M-Noise. Meyer Sound has launched quite recently a new signal, which is more similar to the music in terms of dynamics component, and trying to have a signal that can be reproduced in every laboratory around the industry, which is the final purpose of a datasheet is to have some benchmarking, something that you can check out what this driver can do, but under the same methods and the same tests, so you can compare properly for your application. So coming back to this is a AES power test of a 12-inch woofer with 3-inch coil, and here you can see the blue curve is without Maltcross and the red curve is with Maltcross. So you can see the real increased temperature difference you can get with this technology. Okay.
The just the beginning of that curve, is that fairly accurate? Because it looks like it jumps pretty much like 80% of the steady state temperature within, what is that, a few seconds, basically.
Yes, exactly. This can be less than 1 minute. This is what I was telling you before. Finally, the copper is very good thermal conductor. So the coil, the winding is in almost immediately, in less than 1 minute, you have almost not maximum, but 80% of the temperature you will get with a test like this. Okay. Exactly. And another perspective from this technology, which is important for Beyma, we are finally doing drivers that they must have very good sound quality. Okay, our customers and the applications we are aiming with our transducers are high quality normally. Of course, we have different ranges of products. This is normal, but most of them and the majority of them we are manufacturing with the highest standard as possible in terms of quality, and this is related to the distortion. You know, the sound quality is very related to this part. There are also other subjective parts, very interesting, more related to psychoacoustics, which are related with materials, you know, and other things. But somehow they are also being reflected to the distortions. Okay. So here we have another benefit from the Maltcross. This is just to show you that there is a natural effect in a transducer, in an electrodynamic transducer in this case, which is when the coil is going inwards, the motor structure, the inductance is rising. Okay, so as soon as the coil is going outwards of the magnetic structure and it's facing air, you know, the inductance is going down. Okay. So this asymmetry in the inductance versus displacement is creating non-linearity. Okay, it's this asymmetry in this result is causing a second-order harmonic distortion. Mainly,
that inductance is increasing because there's more iron. The coil's getting deeper into the iron core.
Exactly, it's because the iron to go inwards there are more magnetic permeability, let's say. Okay, so the coil has the electrical current is creating also a magnetic field, you know.
Yes.
So this magnetic field is facing inwards of the driver, a more magnetic permeability, you know, from the iron, exactly, and this is creating this increase of inductance. Okay. So this is what I explained that because what we are doing with the Maltcross technology is to design along with the modulation rings. I don't know if you are related to this technique. The modulation rings are parts that help to modulate the inductance and to reduce also some effects from the eddy currents, which are currents induced by the coil inside the when it's working inside the magnetic structure. So it's very important, as you can see in this design, when the coil goes inwards, you put the modulation aluminum, the modulation ring, which is nailed to the pole piece. So it's helping the inductance to go lower. And when the coil is moving outwards, we have the Maltcross, which is also aluminum material. Maltcross, it's cast aluminum. This is a part which is injected, and the shape and the position is not is calculated in order to have this balance. You can see here below where you have the coil in the rest position is the slotted line. Okay, you have this line, and then as soon as it goes inside, and you have the modulation aluminum ring inside, you have the inductance going down, and when it's going outwards also because of the Maltcross, which is acting in this case also as a aluminum demodulation ring. So here is the comparison. You can see left side, which a driver which has no demodulation ring, no Maltcross, and here on the right side there is a balanced driver in these terms. So this is also helping, as I say, Maltcross, a part of having a very good result, as I saw, with the heat transfer in terms of dissipation, heat dissipation. So having a better, more constant SPL finally, you can also have lower distortion. So this will be, because I don't want to go very deep, as you know, a transducer is very complex device, so we could talk a lot, but just to show you briefly, there these three graphs show some of the most important parameters with large signal. Okay, this The driver is intended to be used with a large signal. Finally, we give the spec sheet with the 1 watt 1 meter small signal domain, which is very important to, as I said before, have a benchmark to, if you want to design a cabinet, to know more or less what should be the size, if it's vented or not, etc. Okay, but then the driver is gonna receive a high voltage and high current in the real application. So these graphs here are showing some of the main parameters we measure and we take into account when we design a loudspeaker. It will depend on the target excursion, it will depend on the power handling, it will depend on the sensitivity. But finally, what we try to do always is to have very balanced speakers in this large signal domain, okay? So here we have the BL versus displacement, which is basically how the force factor goes down as soon as the spires from the coil are going out of the air gap, So it's very important to have it very, very well balanced, of course, in order to reduce harmonic distortion. Also, if you have some asymmetries there, they can activate some DC component issues, some DC offset issues, which I'm sure you have seen. You see a driver moving and suddenly it moves out of the regular position or the rest position, and this can be caused of some asymmetries in this BL versus displacement curve. Then you have the stiffness of suspension. You can see from the compliance point of view or the stiffness. So this is how linear are the suspension system retaining the moving assembly. It's very important also to have it very, very symmetrical and as linear as the application needs finally. Okay.
If it was a perfect ideal spring stiffness, would those just be straight lines going in a V?
Sorry, Simon, repeat.
If it was an ideal spring, the stiffness of suspension, you just idealized it as this perfect spring, would that make it a perfectly V shape with straight lines? It wouldn't be horizontal, right? It would still have a V shape.
Exactly. Well, it depends on the on the.
I guess I'm saying that graph is force versus displacement, or stiffness versus displacement.
The one in the middle is stiffness versus displacement.
I see. Okay.
Okay, so you can see you have in the rest position you have the minimum stiffness because there are no force applied from the suspension to the cone, and as soon as the cone is moving,
the perfect system is a horizontal line. It's the stiffness is independent.
Ideally, ideally, that's right, Simon. Ideally, it will be line. This will be completely linear, But it is also true that you have to sustain, you have to retain the cone from movement. So there is a need to increase that at one point. Well, for instance, imagine, sorry because the graph is not very clear, but here on the maximum number on the x-axis is 10 millimeters, okay? So imagine for a 21-inch, this graph is for a 12-inch, but for a 21-inch, maybe you can have this same graph, but then you have 25 millimeters on the maximum. So this is in line with going much flatter, even flatter, the curve. If you will get the same axis, the same scale right now, the 21-inch suspension system would be like a flat line. You are right, Simon.
Yeah.
So, just to show some results, some objective measurements. Okay, there we go with a 18-inch subwoofer, 4-inch coil. This is a measurement made in our chamber. Okay, so you can see here fundamental, SPL, and then second harmonic and third harmonic. I will show you more graphically now. Comparing a 12-inch without technology, which is the 18P 1200ND, and then the 18 legs 1600ND is subwoofer with the Maltcross technology. So let's say the non-Maltcross technology driver, you can see this is the second harmonic, and you can compare now with the Maltcross, how it drops dramatically. You can see, if we are talking about subwoofer, I would focus in the band between 20 and 100 something hertz, not above, because subwoofer normally goes up to 120, 150 maximum, I would say, okay? So you can see in the second harmonic, there are regions where the decrease is more than 10 dB. This is very, very important, the decrease in harmonic distortion. And it's happening the same in the third harmonic, in the third component. You can see a very important decrease in that subwoofer bandwidth, okay? Mm-hmm. This is the effect of what we've been talking before about the way to design the motor structure, linearity, symmetry with the suspension system, and also with the inductance, where the Maltcross is helping, okay? Another example, now we go to a 12-inch mid-bass driver, and then you can see here the effect is also very, very important. And in this case, the bandwidth I would extend for up to crossing with a tweeter or a compression driver. So you can see the second harmonic is much better in the whole band. And then also it's happening with the third harmonic, especially in the lower part of the frequency. Okay.
The two fundamental curves, one is with Maltcross and one is without.
Exactly.
Yeah. Okay. Just to point that out. I got a burning question about speaker measurements, and this I assume is an anechoic chamber. First, I'll say when I measure, I do headphones mostly. When I measure headphones, even in a reasonably quiet environment, the curve and the low part of the frequency spectrum, let's say even up to 5 kilohertz, is essentially perfectly smooth. There's no ripple in it at all. The driver is this kind of fairly ideal thing. Whenever I see a speaker measurement in an anechoic chamber, there's quite a lot of ripple right throughout the spectrum. What is that? Would that not come out if you put it right in the near field and did a very small signal measurement, you'd see this almost no ripple in that curve at all. Is that true?
Yes. But in which frequency you mean, Simon?
Let's say from low frequency up until, and when you're doing headphones, you'll go to say 3, 4, 5 kilohertz before you see any resonance behavior. Mm-hmm. And that would generally be the air canal. But what I'm saying is that the measured curve is extremely smooth, but for a speaker measurement, it doesn't look like that. Where does that ripple come from?
Well, I must say, in this case, we are smoothing. We are having no smoothing of the measurement.
Yes, here. I know, I understand that. So let's say this driver, I assume it's in a baffle kind of a thing in an anechoic chamber. Yeah, and you've got like a free air resonance is somewhere around the 150 mark, somewhere between 100 and 200. And below resonance, if let's say if you have, should that not be more or less a perfectly smooth curve, but there's a little bit of ripple in there? Where does that originate from? Is that noise from the measurement system? Is that some noise from the anechoic room is not perfect?
Well, honestly speaking, our anechoic room is not as good as could be, of course. It's a semi-anechoic. It's not full anechoic.
Not just yours, it's anybody's speaker measurement tends to have a bit of ripple to it. I was just curious because I do headphones and you just don't get that. You're in the very near field. You have a massive signal to noise ratio. But speaker measurements in free field anechoic rooms, you always see a bit of ripple. Curious.
Yeah, well, you mean from, I don't know, 100 hertz up to 1K, something like that?
Yep, that's what I mean. Or even below resonance. So below resonance is essentially you would expect to see more or less a very smooth curve as it just drops off.
Well, there are some, in this case, because our room is semi-anechoic, and we have a first reflection, and because the IAC panel, we have also a diffraction effect. So we know this is caused in the range between 300 and 500. You can see some irregularity in the response, and this is caused because of that.
Because of what the room?
the diffraction. Yeah, the room is with the diffraction of the baffle, the IEC panel we use for measurement.
Right. Yeah. Okay.
So you have this irregularity. The rest of the irregularities, Simon, honestly, maybe some of them are because of the room. I'm sure there can be some effects due to the different reflections we may have. But I will also say there are some in some speakers we measure. There are some due to the resonance modes we may have in the cone or in the diaphragm. We are measurement. Twitter. But I agree. There are some unwanted issues related to the test, environment, the chamber.
I hate to get sidetracked, but one more point then. So let's take this driver, for example, fundamental resonance, their free field, whatever you call it. Maybe it's 150, something like that. And then at which point would you say is the first modal vibration? Is that this 500 hertz?
Exactly. This will be in this position. Exactly.
Okay. So then the 2K kind of little bump is something like that too.
Mm-hmm. Exactly.
Okay, cool. Sorry, moving on.
Okay.
That's okay.
So, as a summary, the final result from the Maltcross technology is to get more constant SPL output, lower distortion as well. And this technology, as I was showing, can be applied to subwoofers, but also buffers and mid-bass drivers, okay? So we've been working on that for several years now, and we are implementing this to many products right now. And the results are being very, very successful. Some important customers have even asked us to work on some OEM designs, some specific designs with very good results. And this is
are the benefits in the temperature reduction really highlighted in high power speakers? Do you see any temperature saving benefit in lower power drivers? What the reason of this question is, I'm thinking, is there a safety benefit for this? I would think that like install ceiling speakers, because there's a big safety requirement for those. Would there be enough temperature savings to service that kind of market in safety requirements?
Well, it actually where it applies the benefit, if you can finally work and obtain a certain amount of SPL with less power, and it will be better because the temperature of the transducer will be lower as well. So if those installations are being I don't know, if those installations get this benefit, it will be better. I know some applications, for instance, some beam steering applications where the customers are putting several drivers inside a cabinet. This technology is helping because you can get the same SPL with less power applied and less temperature. Okay, but it is true that it depends, because sometimes the temperature that it finally rises the driver compared to the temperature that could obtain without this technology is not so different at the end of the day. I mean, finally the application is looking for high SPL, and it is true that the system will push very close to the real limit of the system.
Okay, yeah, no, just an idea, but okay, please continue.
Okay, just to show briefly some subwoofers family with this technology. We have the recently launched with 3.5 inch, which is because of this technology benefit, we can be working with smaller size coils with the same power handling rating. Okay, so we have the 3.5 inch coil, which is able to handle up to 1000 watts AES, which was normally very, very common for the 4 inch size. Okay, So we have the ferrite and neodymium with this 3.5-inch Maltcross technology. Then we have one step ahead, which is the 4-inch hub with a 1600 watts AES power capacity, which, this power capacity was more related to 4.5-inch or bigger coils, okay? This technology is allowing us to reduce this. In fact, the Maltcross, one of the main reasons why we decided to work on this was because of the neodymium crazy price increase back in 2011. You remember? I'm sure you remember.
The Neo price?
Neo price was rising crazily, during some days.
Yeah.
And then
yeah.
at that time,
I think it went up 600% in 1 year, or something like this. Yeah.
Exactly. It was something crazy. So this was one of the main reasons to start with the Maltcross. And the first product we launched with this technology was a ceramic magnet, ferrite magnet, with 2.5-inch, which was very close, not a completely equivalent, but very, very close to a 3-inch coil neo magnet for, one of the most common applications in our market, which is line array or portable high performance systems, where the neo benefit the low weight of the neo, and the high magnetic flux you can get with this material in the magnetic circuit, was giving a lot of advantages. But some customers and some clients were not willing to continue working with neo in new systems, because that was a certain, a lot of unstable moment for the neo prices. No one knew what was going on, and so we decided to launch some ferrite magnet systems with this technology, able to compete with some neo transducers. And yeah, this was going back to the origin, some of the origins of this. Then, yeah, we've been working also on some multi-layer coil in order to increase the BL factor, the force factor, to have a very well electromechanically damped drivers, for some certain special applications, high performance. And we can also, as I said before, not just for the subwoofers, which is very good for the subwoofers, because as more movement on the air, the better for the convection, for the heat dissipation. But you can also apply to woofers and mid-bass drivers. Here we have 3 different families with different coil size, ferrite, neo, And yeah, we are pushing a lot with this technology because we find it objectively, an improvement in our transducers in both ways, as I said, in the thermal way and also from the distortion and sound quality point of view. This technology is helping a lot.
Okay.
And that's all from my side, guys. This is all I prepared in terms of slides and comments. I hope it was clear. I don't know if there is any question or anything you want to.
I just wanted to pick up on a couple of points. You mentioned earlier on about repeatability is kind of a key thing. What actual level of tolerance can you get? What's possible?
Well,
for big
depends.
Stuff, I don't know about that.
Yeah, no. It depends. It depends on the application. It depends many times on the quality of the materials, on the production process level. There are different. You can be very strict, and you can have very good automated points in some parts of the process, and all of this is finally has an influence. And I can tell you, we have products that can be narrower than plus minus 1 dB, some high top level products, and there are some others that not. But normally, it is also a common agreement between the customer and the manufacturer. Certain applications really do not need plus minus 1 dB, just a few. Maybe some high-end stuff. To
get plus minus 1, do you actually have to sort drivers, or can you actually manufacture a bunch of parts and get plus minus 1 out at the end?
There are some products where we can get that, normally, but because we made a very good job in controlling raw materials, tolerances, controlling, all the jigs, all the quality control in the process, a part of the final OQC. Okay.
Yeah, I've been thinking all along in this discussion that the quality control in your production process must be spectacular to have such a high precision across such a high volume speaker in terms of like its output power.
Yeah. It is true that at the end of the day, my experience is that it is maybe more important to check within the bandwidth, what is the real need in the final application, and where can you absorb some slight differences. Because if you are talking about the crossover region, for instance, it's very important to have a very well controlled response, on where you are talking, I don't know, about subwoofer, it's very important to have very well control of the coil. But at the end of the day, in a certain level of manufacturing, I would say the window, the acceptance window, is not a big issue. There are some regions where you have more unstable behavior, like we've been talking before, like some resonance modes from the cone, and then you can see in the OQC there is a slight increase in the in the variation, and this does not necessarily mean that this is not a good production or this is not well controlled. It is important to know if this is a problem for the final application, then it's there is a need to work on that from the but if talking with the customer.
Also you mentioned you do cone drivers and compression drivers. I've never really understood what a compression driver is as opposed to a cone driver. Could you enlighten me?
Yeah. Well, a compression driver is a non-direct radiation device. I mean, this is the let's say the concept is the same. It's electrodynamic driver where you have the coil and the dome. And then you create a compression ratio between the air which you have behind the dome and through the face plug, which is a device in order to align the wavefront to arrive to, let's say, to cover the same distance and align it in time to have in phase the front wave.
The rear pressure and the front pressure wave.
No, the front, just the front, because the rear front wave from the dome of the compression driver stays in the back chamber.
Okay, yeah, sure.
So it's not it's a way to increase. Actually, this is a way to increase the sensitivity of direct radiation.
So therefore, it's necessarily narrow bandwidth?
Well, it depends because there are some the more recent trend in the compression driver field is to extend the bandwidth. But it is true that depending on the size, the dimensions of the dome, looking, taking into account the main resonances from the moving assembly, and also taking into account the way to design the device, you can get a real wide band. We have, for instance, 4-inch coil compression drivers that can work from 500 hertz up to 20K. Of course, the more usable bandwidth will be in the region between 700 and 12K because of that's where you will get the more linear response. But they can work in a wider bandwidth. Okay.
Right. When you talk about drivers, you refer to coil diameter quite a lot, and so that's one of the key parameters. You have cone diameter and coil diameter.
Well, normally, yes. It's curious because normally the loudspeaker system manufacturers, they are normally defining the systems on the size as well. So it is very common to talk about audio system. I don't know, for instance, a two-way system like a 12 plus 1.4 inch compression driver, 12 inch woofer plus, and normally the names are in line with that size, and this is something.
I mean, I've played with car audio and things like this. I'm very familiar with cone diameter and bigger is better kind of thing. You know what I mean? Just get more volume. But you talk more about coil diameter. For you, is that proportional to the power handling?
Somehow, yes. It is true that maybe this is very, very related to our, our small field, but in the pro audio. But it is true that it's very common when you talk technically about a driver. When you talk about the coil size, somehow we know what range of power we are talking about. This is true.
Would your customers say, I want a 12 inch with 2.5 inch coil? Would that be the way things are specified?
It can be, yeah. Normally, yes. Sometimes they do not. They leave open the size of the coil because they have requirement for power or maybe for SPL. So they leave that. But it is the most common is to ask directly for a coil size and also driver size.
Interesting.
Interesting. Yeah, it is.
Yeah. Any insights in the relationship between the frequency response and the coil diameter?
Sorry, say it again.
Is there any sort of clear relationship between the frequency response and the coil diameter?
Well,
much less of a connection, right? It's very fungible between cone shape and things like that, suspension.
Exactly.
Yeah.
I think it's more related to because the driver is a very complex balance, So when you get a bigger coil size, you have a lot of mass. You increase the mass. Sure. As soon as you increase the mass, you decrease sensitivity. So the bigger coils are more related to lower frequency drivers, lower, buffers, subwoofers. Mm-hmm. You can also you can do a 4-inch mid-range speaker, but then you will probably cone. We are talking about cone, not compression driver, okay?
Yeah, sure.
We're talking about a cone. You should put a lot of energy for the magnetic structure in order to move that mass, So it is true that, the coil, you can do a lot of things on the driver design, but it is true that there are some paths that are not, are better not to go through because probably you can get with another approach, you can get better results, So the coil size, it is true that is normally in our field, it is true that it's related to the power capacity. If you are talking, I don't know, 8-inch or 12-inch, which are very, very common size for the cone drivers, you can find 8 inches in a range from 1-inch coil up to 3-inch. For instance, for the 12-inch, you can start also with 1.5-inch coil up to 4-inch. We have some 4-inch coil designs. So it is true that depending on the final application, for a certain driver size, cone size, you can have very different results with different coil parameters, but always taking into account the mass, always taking into account the resonance, the resonance frequency of the driver, the bandwidth,
Yep. Yep. Excellent. And one more thing, you sort of use categories: bass, mid-range. Where do you put those things in terms of a frequency range?
Well, I would say the bass would work something between the subwoofer, which depends, I would say from 60 hertz, up to, I don't know, 200, 300 hertz. I would
so
say,
in the program stuff, you don't really talk about 20 hertz drivers quite so much.
it is true that the normal minimum frequency is around 40. It's the most common in the pro audio segment to reproduce 40 hertz is, I would say, okay, enough. Of course, you can go lower, but to really reproduce a 20 hertz wavelength, you can imagine how big must be.
Yes, sure. Well, that's the point. It becomes a physical limitation.
There are physical limitations that for a practical professional application makes no sense. If you are building a system in your home, in your house, and you have no compromise, you can do whatever in your I don't know, in your garage, okay? But when we are talking about professional applications, real events, portable solutions, related to that, it is true that 40 hertz, it's something that you can really feel like a subwoofer. So there are some infra bass. They call something like infra bass applications, for professional. I mean, it is interesting. But it is true that the most common is 40 hertz. Simon, you are right. It's not 20 hertz.
Okay.
And mid bass?
Mid bass, I would consider mid bass. It's considered more or less something between 150 hertz, 200 hertz, something like that.
Right. Yeah.
Going up to the mid, even able to cross with a driver.
So that sort of range that you don't feel like you're getting physically shaken.
Exactly. No. Exactly.
Like Dave's a DJ, so he knows all about getting thrashed by low frequency.
But I can't hear you. Yeah, cool. So that's like quite a bit of great detail on Beyma. So I guess so people want to find you guys. It's beyma.com on the internet. Any social media handles, we could always put them in the links below. Do you have any more questions, Simon?
No, that'll round it out.
Okay. Jorge, you have anything else you'd like to add?
No, nothing I'm missing.
Okay, so thanks everybody for watching today. I hope you enjoyed it. Like I said, we'll put the links to all the social media to find out more about Beyma below in the description, and hit us up for questions if you've got anything. And of course, hit like and subscribe if you enjoyed the video today. So thanks everybody. Have a good day.